Okay. So let me know. Can you guys actually see my screen? Can you see Newton's laws continued? Can you see a PowerPoint?
Yes.
Yeah, I can see it.
Sweet. I'm gonna make it ginormous then. So that it looks a little bit bigger on your screen. Maybe. Maybe it's gonna get bigger. There. It got bigger. Wonderful. Okay. So you should have a piece of paper that says complex forces and circular motion, and the first thing on that paper should say friction factoids. Is that true? Is that what printed out?
Yes.
Okay.
Yeah.
Awesome. So look, man, friction should really be one of those things that we have the most experience with in life. You know, we know that friction, it rips tires down, but at the same time, if it wasn't for friction acting on the tires, we wouldn't be able to hold the road. We wouldn't be able to go where we want. So, I mean, if you think about, is friction a drag? Well, sure, it is kind of a drag, but aside from it being a drag, it also really helps us out. So what I want you to write down for friction factoids is I want you to know that friction opposes motion. That's the first thing you want to write down by your box. You don't need to write down all of the things you see here. You just need to know that friction opposes motion. I think it's so obvious, but we never state it. Friction is an oppositional force. It comes from Newton's third law. It is a reaction force to you trying to scrape across a surface. And that reaction force always goes in the opposite motion, just like Newton's third law predicts. The second little factoid that goes by the box is that friction occurs when two solid surfaces interact. So you have to have two surfaces interacting in order for there to be friction. And then the third thing is that we've got drag forces that occur even in fluids. So number one, friction is a resistive force that opposes motion. Number two is you have to have two surfaces interacting. And number three is that when friction occurs in fluids, we call it a drag force. All right, so those are the three big ideas that we need to know. And we're not going to dwell on vocabulary, and we're not going to dwell on writing things down in our unit notes. But number one, you got to know that friction is a resistive force that opposes motion. Number two, you got to have two surfaces to have friction. And number three, when friction occurs in fluids, we call it a drag force. Okay? So what are some good uses of friction? And by all means, don't write this down. Is that, gravity is pulling you down, but what force really pushes a car forward? Like, I want you to think about this for a minute. Gravity pulls the car down, and the normal force keeps the car from crashing through the surface. So we've got a car's engine, and that engine pushes backwards, and friction pushes us forwards. I know that seems so weird, but that's in reality how we get forward. You got to push backwards really hard to go forwards really hard. So we need to write down the two types of frictions. And the static friction is the friction that keeps an object at rest. That's what I want you to know for static friction, is that it's what keeps an object at rest. So when we do calculation problems, we've got to keep track of who's static and who's kinetic. That's the big one, okay? Static means I'm not going to let you move. When you first start to push on something, it doesn't move at first because of static friction. But then once it's moving, you still got to deal with friction. And that's called kinetic friction. And that's why my PowerPoint says there's a guy pushing a refrigerator. At first, refrigerator doesn't move, the refrigerator doesn't move, the refrigerator doesn't move. Oh, it's finally sliding. And now look, it's easier to move. but it's not without force that you have to apply to make it move because there's a kinetic component to it. All right, so we call the differences, we literally just call one static and we call one kinetic. Okay, don't write down this stuff, but the static force equals the applied force for as long as it can. That's Newton's third law. But then after that, when the object overcomes that static force, it now encounters friction force that is considered to be kinetic. All right, so we need an equation, and the friction equation is the fun equation. This is an equation you can have fun with. So the authors of your book write friction static, so F S of F or F K of F, like Kentucky Fried Chicken, and mu static, mu kinetic. It's all the same. It's all the same. All right, it's the same equation. It just depends on, are you not moving or are you moving? Lots of people put that S in there and incorrectly think that's for sliding friction. Kinetic energy, kinetic motion. Kinetic is Latin for moving. Static means I'm stationary. Stationary comes from the word static. So we've got two cute equations, but they're the same equation with different subscripts. That's it. And a little side note, friction only depends on the materials you're sliding against, not the surface area, but that's no big deal. What is this idea called coefficient of friction? You probably remember from last year that the coefficient of friction, it's a constant that varies per material. So asphalt has its own coefficient of friction when rubber slides against it. Asphalt has a different coefficient of friction when metal slides against it. So you have a couple different coefficients that can be at play. All right. So what I'd like to do right now is let's just practice working a couple problems. All right. I've got a 1,500 Newton crate that's being pushed across the level floor at constant speed. And boy, you're going to hear constant speed a lot, and I'll explain why as this problem progresses. So we are pushing this 1,500 Newton crate by a force of 600 newtons, but that force is being pushed at an angle. All right, so let me kind of lay this out so we can make our picture look like the one that's on your paper, and then we'll answer that. What is the coefficient of kinetic friction between the crate and the floor right here? So let's see what this should look like. A free body diagram will really help us here. So our free body diagram would look like this. That's going to be the weight. That's 1,500 newtons. Now, what I also know about that is I'm going to have that's 600 newtons. So, what I need to do is I need to figure out as with any problem that gives you an angle, your first job should be to figure out the force in the y and the force in the x. So I'll grab the calculator and I'll help us out. And this is 20 degrees in here. So cosine of 20 degrees times 600 is going to give us the f of x. So our f of x equals 564 newtons. Our f of y, which is negative sine 20 times 600 newtons, this is negative 205 newtons. It's so important to understand that we have components on here because these x and y components are going to change how we write our equations. So we know. Let's do the sum of the forces in the x dimension for this problem right here. The sum of the forces for this would be the force applied. Oh, here. Let's write it down first. Sum of the forces in the x dimension would be the force applied minus the force of friction. It equals 0. Why does it equal 0? Constant speed. Let's look at the sum of the forces in the y dimension. Well, we've got a normal force that goes up minus a force component in the y minus the force of gravity. And that also equals 0. So do you notice that in the x dimension we've got 2 variables? And in, is my smartboard not writing actual numbers for you guys? Like I'm writing on my smartboard. Is it showing up for you all?
Yeah. Like you can see it, it's just in the 2 little screens.
Oh, that's weird because it's not even showing up on my computer. It's showing up on the smartboard. Is it too small to see or is it okay?
It's fine. I can see it. I can read it.
Okay, good to go. Thanks. I just wanted to make sure you were seeing anything. All right. Wonderful. So what am I supposed to do with this? Well, here's what we really need to do. We got to do the y equation first. And I'll explain why here in a minute. So the normal force equals Fg plus Fy. So let's figure out what the normal force is. The normal force will be 1,500 plus $205. What? That's right. The surface has to be able to push up with 1,705 newtons because that 600 newtons is kind of pushing that box into the table. And the weight is pushing that box into the table. So the normal force has to push up with 1,705. All right, all right, all right. So now that we know the normal force, we can solve our problem. Because our problem can be solved with this. The force of friction equals mu F of n. If we're looking for the coefficient of friction, then we know from this equation, now we go to this equation, and we know that the force applied equals the force of friction, and the force applied equals our x component, 564. Now that we have all that figured out, and you got a lot more space than I do, the force of friction would be 564 newtons equals mu, and then our normal force is 1,705 newtons. So we're looking at 564 divided by 1,705. Bam! Mu equals 0.33. All right, ladies and gentlemen, I hope that helped out. I hope that worked. I was hoping all that writing would show up. Well, it did for a split second. I don't even know. So there. There's exactly what I did laid out. There. Okay? That's kind of a linear way to do it, but I explained it. We have already talked extensively about inclines with friction, so I'm not going to talk about this again because we've already gone down this road. The important thing to remember about an incline is that we have to change our orientation to match. And the biggest thing to remember is mg sine theta and mg cosine theta. Those ideas right there are components of weight. And this angle equals our apex angle. Okay? So what are my tips for solving this? Let's call this the x-axis, and let's call this the y-axis when we're solving problems, and let's write equations that would solve them that way. Okay? So let's look at your core problem 2 on here. Okay? Your core problem 2 says a 3 kilogram mass slides down an incline where friction is present. It does it in 4 seconds. It wants you to determine the acceleration of the mass. Well, we know that m2g goes down. Look, this is kind of like our journal we did today, right? This is just like the journal we did today. And we have our components. So let me give you all a chance to catch up with your drawings. When I put a mass on an inclined plane, the normal force acts up, which is what Cauchy said. Pre said the force of friction acts up the ramp. Cole said the tension acts up the ramp. Calvin said that weight force has an X and a Y component. Let's not get away from what Isaac Newton said. Isaac Newton said, as far as this sliding down the ramp goes, F will always equal ma. But it's an unbalanced force in the x dimension equals ma. So what gives this an unbalanced force? Well, we've got to have a consideration for the weight component that acts this way and a consideration for a tension component that would act that way, or consideration for a force component that acts this way. Now, this problem does not have tension in it. All right, this is a particular problem that does not have tension in it. Because this problem doesn't have tension in it, then we can just go ahead and forget about this. See, that just didn't happen. We don't even need to worry about that one. So I'm going to stricken that out on here. No reason to worry about that. But let's talk about the two that it does have. Okay? The two that it does have is it has, and we're going to call downward positive acceleration. Okay? So we're going to say that the we're going to say that this mg sine theta, or this g of x, acts down, and then the force of friction acts up that way. And that equals ma. Well, what is the mg sine theta? It's this. Well, what is the force of friction? The force of friction, you've got to substitute in the fun equation. The force of friction equals mu and then n. N is mg cosine theta. So look what we've done. And I know we got some of this in that University of Cincinnati problem, but I just thought you might like a little more detailed explanation. We're not going to solve this problem. We're okay not solving this problem. All right? Because we can go on and solve this just like this. We can find the acceleration using a kinematic problem, and then we can plug the acceleration in and solve for this. So, there we go. If you guys want to write that down, go ahead and write it down. This is the type of problem you can expect on an AP Physics C test. It is a problem that tests what you know on vectors. It's a problem that tests what you know on making a net force equation match a free body diagram that you drew with the vectors. It is a question that makes certain that you understand the big five kinematic equations. And then it's a problem that's two-step that makes sure that you know how to use substitution to solve for an answer. There's no calculus involved. If they wanted to make calculus involved, they can say that the force of friction is a variable force, and that force varies as a function of x squared plus t squared minus 3. And then we could integrate that function as a function of time and then calculate an acceleration, and it could ask for a specific acceleration at a given point. But we don't have to do anything like that on this problem. All right. Any questions out there? Because I know we're pretty good at solving these problems, but I don't want to not talk about something if somebody has a question. So everybody good? All right. Everybody's good for right now? Underneath limiting angle of repose, I would just like you to understand that if you put a coin on a book, then eventually that coin will slide. Like as you lift the book up and up and up, that coin will slide. Well, do we know exactly where that coin will slide? Well, we can look at it through its limits. So let's look at the limits in the x. And that would be fgx minus f sub s equals 0. What does that mean? Well, that means the component of the mg that goes down the ramp is going to equal the force of static friction. Static. Let's look in the y dimension. Well, the normal force is going to equal mg sine theta. Well, we just did that too. Well, look, if those are correct and we now do substitutions, for instance, we say mg sine theta equals f of s. And then we say mg cosine theta equals f of n. And if we plug that back into our fun equation, we get a mu that says something will stay stationary on an inclined plane as long as the mu is equal to tangent theta. So you do the tangent of theta and you find out the mu, you found, for that coefficient of friction, you have found the magic angle. That's simple. So every surface has its own limiting angle of repose. If 0.1 equals tan theta for a book in metal, if it was metal on concrete, that would have a different mu. Well, then that would be a different angle. So I think you guys see how that works. So if you hear the word limiting angle of repose, just think mu equals tan theta, and you move on with your life. That's exactly what you do. You move on with your life. Y'all are doing wonderful. Y'all are doing wonderful. Okay. So we are not going to delve into this world anymore with drag force or anything like that. So I'm going to segue out of this slide. I'm going to back that down, and then we're going to do this. And then I'm going to open up this right here. Because when it comes to circular motion, I'm going to give you the quick and the easy route. Now, did your worksheet print out did that worksheet have two sides? Did one side have centripetal acceleration equation, speed, and periodicity on it?
It has 3 sides.
Oh, sweet. So it's a biggie. All right. Well, then you tell me, is there a place to write these 3 at the top of one of those pages?
Yes.
All right, beautiful babies. So look, man, here's what I'm going to tell you. And I'm going to give it to you easy, just like this. Isaac Newton said that nothing can go in circular motion in this entire universe. Everything in this universe goes in a straight line. Everything goes in a straight line. The only way something can go in a circle is if you apply an outside force to it. All right? So you tell me, what force is making that satellite right there go in a circle? What force makes that satellite go in a circle?
Gravity.
Okay, if there's no gravity, that goes in a straight line. What force is making these NASCAR cars go around this circle?
Friction.
Friction. What force is making that tether ball go around a circle?
Tension.
You got it. What force is making that dog go around a circle? Oh, he's not going around a circle. So there you go. Ladies and gentlemen, the equations are very simple. They'll be provided on your AP Physics C exam. Centripetal acceleration is v squared over r. Mr. Matthew, why is it v squared over r? Can you explain to me what derivative made that? Maybe here in a little bit. Not right now. How do I get the speed and periodicity of something that goes around a circle? Easy. What's the distance of the circle? 2 pi r. What's the time to go around the circle? Capital T. Capital T means a special time period. It means the time to do one complete circle. That's periodicity. How do I calculate a centripetal force, Mr. Matthew? It's mv squared over r. Well, that's sweet. That works out. That's perfect. Now, ladies and gentlemen, this is going to be, yeah, I'll get this. Got it. Ladies and gentlemen, this is the part of the show where I let you go. I don't need to walk you through all of these things, but I'm going to let you do these unit notes on your own through my Weebly. But I am going to take the opportunity to explain 2 ideas to you. If you have ever been on one of these tilt-a-whirls and you find yourself spinning, it's hard to imagine that you feel a need to get accelerated towards the center of a tilt-a-wheel. But the reason why is because acceleration is a change in velocity over time. Now, look at these 2 cars on the tilt-a-wheel. These people believe they're going to get ejected that way. These people believe they're going to get ejected that way. So what would be a final velocity vector minus an initial velocity vector? Well, let's put an origin right here and say that the final velocity vector minus the initial velocity vector, and if you say minus, that means you have to flip directions. Look at where my origin is. If I go final minus initial, my vectors change, which is indeed itself a derivative. Makes me feel like I'm getting accelerated this way. So it's really vector calculus that describes why we feel like we're getting accelerated towards the center of a circle. And why do we get to v squared over r? Look, man, how in the world can an acceleration not equal a change in velocity over time? It does. This vector minus this vector gives us this change in vectors along an arc length. And when we take a derivative of angles to time, that gives us a v over r. So if we substitute the v over r, oh my goodness, look at this. You will never need to know how to do this. But that's why it's not simple to just find v squared over r using regular equations. Your task is, over the course of tomorrow, fill in the rest of this worksheet. The rest of this worksheet, you're going to want to fill in these ideas right here. And I'm going to put some things on there that are going to help you. All right, I'll put on, I will add more things to it. But for today, you're done. You don't have to do one more thing for physics today. we will talk about this stuff on Thursday. Like, we're going to talk about the conical pendulum on Thursday. So people, get your notes updated to the conical pendulum. We'll talk about it. We'll do a little simple lab, and then we'll try to really get good at circular motion here coming up. Well, I'm telling you, that was definitely a mouthful, and you guys did a great job hanging in there. Are there any questions that anybody has about anything? Wait, what's that?